Good afternoon, Year 11. I just suddenly realized I was going to say good morning. And then I was like, hang on a minute. It's afternoon by like 20 seconds. Good afternoon. Sorry. I just went supersonic then. I was just pausing my other... Wow, pause that on a really bad session. There we go. Just turning that down so I don't want that to be running. Hello. Right, I've got a couple of people watching. If you can say hi on the chat, that would be great. It's always good to get some feedback and make sure that you guys are here. I'm doing the second part. So yesterday we went through questions 1 to 9 on the 2015 regional paper for iGCSE Chem. I hope you found it useful. I hope you had a chance to kind of look at those kind of sections. I know that Irina was asking about how I teach rates of reaction using a process called Kick-Ass. It's worthwhile looking through my webinars on rates of reaction if you've never seen that. Also, coughs in equilibrium. Hey, Ira, Evelyn, thanks so much for coming. Great to see you. Thanks for coming. Hola. Right, I'm basically just gonna crack straight on. Oh no, thank you, Ira, for coming along. I really appreciate it. It's really nice to see you. I hope you guys are staying well. Hey, Rita, nice to see you. Oh, it's nice to see you for the second time. That's great. Right, so let's finish off. Hey, Marella, lovely to see you. Thanks for coming. We're doing well. Right, I'm going to share my screen. Let's give this a whirl. Share screen, and then click on that one. There we go. I'm going to hide that bit. I will also then turn off my camera. Because I seem to find disable device. I seem to find that it was behaving an awful lot better, wasn't it, after I had done that? It was just obviously running it in the background. Right. Okie dokie. So let's crack straight on with questions 10 to 15. Let's get it moving. Right. So we left off last lesson. This was the end of part 1. And we had just finished running a basic calc. And there was a really lovely equation for bleach. By the way, that's actually mild bleach. That's under cold aqueous conditions. That's actually part of the A-level specification. There's Edexcel drawing on it. It was really nice because there was no difficulty here with this equation. You just literally they were testing your ability to just take things out of the question and put them all together in balance. That's all they were testing on that one. So then we ended at that point and we came to number 10. Okay, so it starts off with a gas collection process. Oh, by the way, these diagrams are one of Edexcel's specialities, which this particular piece of apparatus up here, this is called a tap funnel. It's what that's called. It's called a tap funnel. Tap to set up a pen. No, I don't want you to set up a pen. Go away. Yeah, this is called a tap funnel. The reason why it's called a tap funnel is because there's a tap. There's Edexcel. Hey, Julian, great to see you. Thanks for coming. Really appreciate it. Edexcel's speciality of... Alexa, stop. Sorry, Alexa was chiming in there. Edexcel pull these bizarre pieces of equipment out. Hang on, just turning Alexa off. There we go. Sorry, folks. Sorry about that. Hey, Liz, thanks for coming. Another one that they did is another piece of apparatus called a thistle funnel, which is a rather odd one, which was like this. There you go. It's called a thistle funnel. It's called a thistle funnel because it's got the head shape of a thistle. It's like got this round bulbous end and then these points at the top. And yeah, this is called a thistle funnel. Go figure. I've never seen an exam board quite like Edexcel in their bizarre pieces of equipment. And all they asked you to do was to label it. You didn't actually have to know the name. It was like you pulled it out of the question, but I was still a bit kind of like, well, a little bit unfair, especially if people don't know what a thistle looks like. Bit tricky. But yeah, this one's called a tap funnel. These pieces of equipment are designed to be able to add liquids without the worry of splash. They're far safer to use. Whenever I do a gas prep, we use a tap funnel because it allows you to add it in small increments. They usually have a scale up the side like this, so you can actually see how much you're adding. They're rather nice pieces of equipment. We've got a few in school. But this is a classic gas production, and it says this apparatus is used to produce hydrogen. Write a chemical equation for the reaction between zinc and hydrochloric acid. Okay, so by the way, it says include state symbols. Oh, very interesting. So we've got zinc metal, which is going to obviously be a solid, and then we're going to add it to hydrochloric acid. Now, this is where the test is. Lots of people, there's the very common habit of putting acids in as liquid. Remember that there are no such, well, there is a liquid acid, and that's under concentrated conditions, but you never see it at iGCSE. Acids are always aqueous. Hey, Sian, lovely to see you. Thanks for joining. We're then going to form zinc chloride. Now, just to tell you that zinc is always a +2, just so you know. Yeah, it's one of those ones which you can't get that from the table either. I'm just going to check that. I'm suddenly thinking I might not have a periodic table on hand. Nope, that's frustrating. I need to grab one. Let's go for iGCSE periodic. That didn't work very well, did it? I don't really want PDF. Let's just go for images. Zinc. Yeah, you've just got to know that one. It forms a +2. Sorry, folks. That's awkward, isn't it? Yeah, zinc's a +2. Sorry. That's a bit of a nightmare, isn't it? I'm trying to find one that's a reasonable size. Taking too long. Anyway, zinc's a +2. Does it give you any hint at that? It really doesn't. Go figure. And you have no ion table. Hi, sir. Sorry I'm late. I slept in late. Hey, Tom. Good to see you. Yeah, sorry about that, folks. You just got to know that zinc. Oh, and I nearly forgot state symbols: aqueous and, of course, hydrogen as a gas. Yeah, zinc's a +2. Add that to your list of ions to learn. Silver is always key ones to remember. Silver is always a +1. Lead is always a +2. Mercury is always a +2. Zinc is always a +2. What other ones do you need to know of the actual metal ions? I think that's it. I think. Titanium +4? Maybe. Anyway, good things to just to remind you guys of course, and all your complexes that you've got to learn all your complex ions. Remember NOx, nitrate, hydroxide, carbonate, sulfate. And remember, I do these ones to try and help you remember the order of these SO4, 2-. The top two are both 1-. The bottom two are both 2-. And the carbonate is in position 3 to remember the oxygen number, and sulfate is in the position 4 to remember its number. Yeah, that's just how I tend to teach it. But those you've got to make sure you remember. State 2 observations you would make during the hydrochloric reaction with zinc that's interesting, in the conical flask. So what are we going to see? We're going to see fizzing. So when the acid goes on top, we're going to see fizzing, going to see bubbles. Yeah, you can say effervescence if you like, if you can spell it, no problem. But we're certainly going to see fizzing in it. Yeah, and what else are we going to see inside it? We're going to see the zinc metal disappear. Was the acid in excess? No, don't really know. But we're certainly going to see the metal disappear. Yeah, metal will disappear. You've got to say what's happening. It's got nothing to do with this side. Nothing to do with it. Yeah, they're saying what we're going to see happen inside the conical flask. Metal will disappear. Or shrink in size. Yeah, very reasonable to say that, to shrink in size rather than say disappear. Next, good old, I know that you guys have a real issue with these. So the diagram shows the final reading on a burette. Now remember, on burettes, you read top down. That is super important. Yeah? So this is going to be, let's zoom in. I know you can't do this on your exam. That's 10.1, 10.2, 10.3. This is 10.4, but we're about to lose the mark, aren't we? Because on a burette, it even tells you, gives you a hint in the question. Just reminding you. So that is actually going to be 10.40. It's really important to remember that second decimal place. When that line there, that curve, I'll highlight it rather than drawing on it. There we go. So the line there is sitting exactly on the 0.4 line, which means that's 0.40. If it was sitting between two lines, yeah, if it's sitting between them, remember, we ignore the tail in. Yeah, you read it from the bottom of the meniscus. Yeah, so that there is in between it. So that would be, 0.4, 0.5, 0.6. That's 0.65. 10.65 is what that one would be. So just watch out for those traps on burettes. It's one of those ones which comes up year after year, and you do need to make sure you're focusing on it. Oh, look at that. Both have given a 0.0 value. That's interesting. Right. So experiment number 1. So she fills the burette to 0.0 mark with dilute hydrochloric acid. She places 0.5 grams of zinc in the column and adds the acid until the reaction is complete. The diagram shows the final reading on the burette. Right. So it says experiment 1. Notice that the final's first and the initial and then the vol. So the initial, of course, is 0.00. If you put in the number 0 there, you're going to lose the mark. So be careful whenever you're doing titration data, it must go in to 2 decimal places. Be careful. So initial reading was 0.0. They told us that. And then the final reading is 10.40. 10.40. So the volume taken, the volatile was 10.40. That's nice. It keeps it nice and easy for us. Right, experiment number 2, initial reading, 1.90, reading top down, 1.90. If you forget the 0, you lose the mark. Final one, 22.1, 2, 3, 4, 5, 6, 7, 70, 22.70. And I'm going to have to do a bit of maths on that one. I'm not going to do that in my head. I have seen and made too many mistakes in the past by doing those kind of easy mathematics in my head. 22.70 minus 1.90. It's just not worth it. Wow, big difference. Just going to check that reading. It's a very big difference between the two, experiment 1 and 2. The concentration of the acid in experiment 1 was 0.74. Explain how the concentration of the acid in experiment 2 can be calculated. That's interesting. Okay, so we know how it can be. You can work out the moles of zinc, but they added it till excess, until the reaction is complete. She then repeated the experiment with the same sample, but with a different sample of acid. Use the burette readings to complete the table, record the volumes. The concentration of the acid in the experiment. Right, hang on a second. How did she get that number from that value? How did she do that? Hang on a minute. And they're looking for the concentration. Hang on. Number of moles equals C times V over 1,000. Well, they've got... And the volume... hang on a sec. So if I do that concentration, 0.74, and a volume, which we have from the first one, 10.40, all over 1,000, that'll give me moles. Explain how the concentration of the acid in experiment 2 can be calculated. 0.74 multiplied by 10.40 all over 1,000 gives me 7.696 times 10 to the minus 3 moles. Right, hang on a sec. If we now put that number back in, but now we've got a different volume, yeah? So reorganize this equation, number of moles times 1,000 over the volume gives me concentration. So, wow, that can't be right. It just does explain how. Calculate the moles. Well, that seems awfully complicated. Explain how. I feel like I just want to run it through. I mean, obviously it's going to be, it's twice. It's, guys, the volume's exactly twice. I just didn't see it. Took me a while. Wowza. So if it took twice the volume, it's going to have half the concentration. So you just need to do 0.74 divided by 2, and that's it. 0.74 divided by 2. 0.37 moles per dm cubed. Huh. I wonder if my other way had given me the same number. 7.696 exponential minus 3 multiplied by 1,000 divided by a volume of 20.80. And I get exactly the same number. Lol. But they want you to explain how. How strange. 2 marks. Want to see the mark scheme for that? I'm just going to say it's got twice. So the volume is twice. Therefore, divide the original concentration by 2. I'm assuming that's what they want. How fascinating. Let's have a look. Wowza. That's the first question, folks, where I've been genuinely like, oh, that's 2 marks. Now that I'd like to see a mark scheme for. What would I write down in an exam? Well, I'm going to give my answer. Yeah, I'm just going to say bullet point number 2, volume of acid needed is double compared to first, compared to EXP experiment 1. So concentration is half. So concentration is half experiment 1. Let's see what the mark scheme says. How fascinating. Really, that's the first one where I'm like, yeah, okay. Now I want to see the answer to that. 2 marks. Because the volume has doubled, the concentration is half. There we go. Wowza. That really took me by surprise. There's the first one where I was like, ooh, that would have been horrible for me to have gone further on that. Draw the displayed formula of the monomer. Oh, we're always liking these. Guys, you have to know this one. This is called PTFE, polytetrafluoroethene, otherwise known as non-stick. This is in your pans, folks. So to turn a polymer, by the way, Edexcel's allowed to do it. You shouldn't. There you go. That's the real picture. Yeah, that's the repeating unit. Yeah. What we want to do is take away the bonds outwards and put the double bond back in. That's it. So I'm just going to redraw that. C double bond C. So it's now become unsaturated, and that is called tetra, being 4, tetrafluoroethene. And in the polymer, yeah, the polymer is you break the double bond, break the double, and then put them out that way, and that becomes polytetrafluoroethene. Gotta love it. Explain what the term polymer means. 2 marks. A polymer, bullet point number 1. A giant molecule made from many, there's poly, there's your poly, many repeating monomers. There you go. And I know that, by the way, lots of people have gone many parts. It's not sufficient. You've got to pad this out, folks. It is a giant molecule made from many repeating monomers, many repeating units. I just want to check the mark scheme again. So that's 2 marks, you see. Need to see it. Except large molecule, except macromolecule, that's okay. Except formed when small molecules join together. Except react, bond, add, link, join. Oh, okay. Formed when many join together. Made from, I'm going to be really mean to myself and not give it to me. Yeah. Made from many repeating monomers, all joined together. I feel like it's the joined together bit that they were after. Yeah. Definitely not going to give myself that mark, folks. Yeah. I'll be mean to myself. It's all about being strict because you're making those adaptations, remember. I'm going to highlight that. That's a bit I need to make sure I add. Made for a giant molecule made from many repeating monomers all joined together in one structure. Suggest the name of this polymer, polytetrafluoroethene. Polytetrafluoroethene. Now, what I'm really interested about is, there it is. They did give you the name that you just needed to stick poly in front of. If they hadn't given you that, and you know what? I wouldn't put it past Excel to not do that. Be wary. Give the name and molecular formula of the monomer used to make this polymer. All right. So 2 units, 2 units, 2 units. There we go. That has 5 repeating units, and the repeating 5 repeating units, and they're all the same. Take one apart and put the double bond back. This is ethene. Easy to do. There you go. So the name of the molecule, give the name and molecular formula of the monomer used to make. So name is ethene. Molecular formula, C2H4. I like it. Explain how addition polymers that are buried in landfill sites remain chemically unchanged for many years. Okay. So we're going to say 2 bullet points. Number 1, addition polymers are non-biodegradable. I think everyone's going, yeah, I got that one. Biodegradable. Yeah, we know this. That's easy. But now we need to go a little bit further. Therefore, they are non-biodegradable, so can't be broken down, into smaller parts. Yeah, can't be broken down in small parts. I think that would probably be okay. I'm also going to say this is because, I'm just going to state why. This is because the carbon chain bonds are very strong. That's in reality why. If you want the A-level bit, it's also because they're non-polar. If you want that bit as well. I just want to check the mark scheme now for that one. Horrible questions. Do not biodegrade. They are inert. Do not react, unreactive. Okay, so except not broken down by bacteria, ignore, do not react with any named chemicals. Oh, ignore reference to bond strength and bond breaking. There you go. They are inert and unreactive. There you go, guys. Even I'm making corrections here. I think it's totally reasonable. I always like you to see the honesty that I always have. I never, ever, it's not like I go through this and ensure that I always give the right answers. You know, I need to make those corrections as much as you do. So when I'm teaching this, I'm reinforcing those particular points. So they are non-biodegradable, definitely got the first mark, but we also need to say, well, biodegradable is talking about the breaking down of bacteria. We also need to say that they're inert. Yeah. What that means is they're not going to react with things like water or oxygen. Yeah. This is bacteria. This is oxygen and water. That's what they're doing. Yeah. Really good question, though. Oh, there we go. Right. A student count reactivity of metals. Name the substance that causes the brown coating on the zinc. Right. Zinc, brown coating on zinc. Oh, it's reacting with copper. So this is copper nitrate. So you're forming copper. I'm actually going to say name the substance that's, copper metal. Yeah. So just to tell you what's happening, yeah, the zinc is displacing. The zinc is more reactive than the copper in copper nitrate. So what I'm forming is zinc nitrate and copper metal. Yeah, and I'm seeing it go pink because I'm forming copper metal on the surface as a solid. Yeah, and copper's pink. Or they've said brown here. State why there is no change in the experiment with zinc nitrate. They've put zinc nitrate in with zinc, strips of zinc. Well, zinc can't displace zinc. Yeah. Zinc, I shouldn't do shortcut in that case. Zinc metal doesn't react with zinc nitrate. I'm being naughty and doing formulae. Zinc nitrate due to same metal, therefore, comma, same reactivity. No reaction. Reactivity. There we go. I want to check a mark scheme again. Copper. Zinc cannot displace itself. Zinc cannot react with zinc ions, stroke zinc nitrate. Okay. Except the two metals involved have the same reactivity. Nice. So it cannot displace itself. Okay. Fine. Next. Put them in order of reactivity. The student repeated the experiment with strips of metal M. Okay. So, metal M with metal, well, that's obvious. Idiot, that's just a waste of time. And then metal M with zinc nitrate, no change. Right, metal M is above zinc. Gonna give a nice big space for myself. If I was in an exam, I wouldn't have that much space. I'm gonna do it here. I'm gonna go zinc and zinc nitrate. Oh, no, metal M is above zinc. Yeah, because he added metal, he put metal M into zinc nitrate. Yeah, I shouldn't do that. Zinc nitrate, and nothing happened. There was no change. So what that means was, oh, hang on a minute. The metal M went into zinc nitrate and there was no reaction. No reaction, which means that zinc is above M. So easy. That's why you've got to think this through so easily. It came out in the wash, but easy to get the mistake because M didn't displace zinc. Zinc didn't appear. There was no reaction. Okay, so we've dealt with that one. Next, we put metal M into copper nitrate and a brown coating formed. Right, so we put M into copper nitrate. Yeah, we put it into copper nitrate and we've just formed copper metal and M nitrate. So M is more reactive than copper. So copper, it must be down below M. Get this, okay? Last one. The question is, where does the last one go? Yeah, so we've done him. Right, aluminium nitrate, no change. Right, so aluminium, they've put metal M, hang on, we've put a metal M with aluminium and no reaction. Aluminium is above M. Now that's interesting. Guys, there's a problem. So it either goes above the zinc or below the zinc. Wow. That's use the information in both tables. Okay. All right, so there's obviously more data. The answer is aluminium's above zinc. There you go. There's the zinc. There's the aluminium bit you need. Okay, so Al, Zn, M, and Cu. What's the mark scheme say? Al, Zm, copper. Okay, done. Oh! That's interesting. Do they allow the symbols? Do they allow it? Ignore symbol. Reject, ignore symbol. That's really mean. The question's rather ambiguous on that front, guys. Use the information to place the metals, aluminium, ignore symbol. Wow. That's really mean. Very interesting. Then it was zinc, wasn't it? And then it was M. and then it was copper. How strange. Interesting. Next. Oh. It's just loading. It's thinking about it. There we go. State why this reaction is described as a redox. Right, so magnesium is losing electrons. So redox, yeah, reduction. Reduction is the gain of electrons, Rig, yeah. And oxidation is oil. Oxidation is loss of electrons. Right, magnesium is losing too. Mg, magnesium, is losing 2 electrons. And silver is gaining 1 electron, and silver is gaining electrons. It's gaining electrons, both happening at same time. We're done. Oxidation and reduction are occurring simultaneously. Next, explain in terms of electrons which species is behaving as an oxidizing agent. Oh, right, oxidation is loss. The magnesium is being oxidized. Yeah. So the person doing the oxidizing is Ag plus because it's being reduced. That's really hard. Just to show you there's a trick to this, guys. Those people who won't get me for A-level if you go to a different school or whatever. Yeah, right. I'm teaching you an A-level trick, redox. So in A-level, it gets a whole lot more confusing. This gets a bit more complicated. And what I invented, I love oil rig. Oil rig is amazing. Yeah, oxidation is the loss of electrons. We know this. Yeah, ox is loss of electrons. And rig, reduction, red, is gain of electrons. We're okay with this. Well, I invented a picture to make this easier for when you get to what's called oxidizing agents. And this is just edXL pushing you to your A star for your GCSE. Metals, most of the time in redox, we're talking about metals. It's not always the case, but most of the time. And I wanted to say that metals lose. So I invented a picture. So the arrow is showing that the M is losing the electron. Yeah, and the agent is therefore gaining it. This is an oxy agent, just for the future reference. So therefore, metals gain electrons, and a reducing agent, a red agent, is therefore losing it. Yeah, the metal is gaining it, the reducing agent is losing it. So they've just asked us to describe, in terms of electrons, which species is the oxidizing agent, the one gaining electrons, and that's silver. Yeah, Ag plus is the oxy agent. I wouldn't do that in a real exam. I'd write oxidizing agent due to it gaining electrons. We're done. You can't write that down in an exam either. You have to write down the word electron. Sorry, bad habits. Name the piece of apparatus used to measure nitric acid. Put 25 centimeters cubed in a beaker. That's a measuring cylinder. Not going to waste your time with that. Measuring cylinder. How would the student know when she had added excess zinc carbonate? Yet she would see no more effervescence. Yeah. No more bubbles would be present. No more bubbles seen. I want to check that answer. What's that say? Checking a lot. Measuring cylinder, no more bubbles. There you go. Name the separation method in step 3 to separate dilute solution of zinc nitrate from the mixture. They're trying to make zinc nitrate crystals. So the zinc carbonate, until it is in excess, separate the dilute of zinc nitrate from the mixture. So it's filtration. Yeah, we're going to filtration. We're going to remove. We've got a beaker with leftover zinc carbonate in it. We need to get rid of him, filter it. The student wants to obtain a pure sample, 4 marks of a hydrated. Right, this is one of our stories, folks. One method is to leave the student out of the water to all evaporate. Describe another method involving crystallization that the student could use. Right. Evaporate 80% of the water. The water using, they're probably going to want equipment, using an evaporating, I should have spelled evaporating wrong. Evaporate. Using an evaporating dish. Using a glass rod. Use a glass rod to see if solution is saturated. Leave to cool down. So crystals form. You've got, the great thing is you've still got 20% of the water left behind, which means that's going to be trapped in the crystal, forming hydrated. Yeah, so leave to cool down, so crystals form, and then filter out crystals, and dry. Mark scheme. Heat, boil to partially evaporate the water. I like it. Next, leave until crystals form, filter. Appropriate method for drying, using paper towel. And dry. I'm going to do that in a different color to emphasize that I missed it. Yeah, and dry with paper towels. They actually wanted a method for drying. Go figure. Very common though. Right, into bonding. I like it. We've got giant ionic lattice, and we've got giant covalent sand. Explain how silicon dioxide, why it has a high melting point. Susan Boyle sings Nelly the Elephant. I know it's only 2 marks, but you've got to, folks. Yeah, structure of SiO2 is a giant covalent lattice. Giant covalent lattice. I'm running what's called Susan Boyle sings Nelly the Elephant. These are just a method of getting all the marks. Structure is a giant covalent lattice. Bonds are strong. I'm actually getting that third one. I've only got 4 lines, you see. Strong covalent bonds only. Number, so I've just gone tick, tick. Yeah, number. There are millions of bonds. See how I blended it to match the lines? It's the only adaptation. It's quite a nice thing to see that though. Bonds are strong covalent bonds only. Yeah, I've just picked up both the strength and the bond type, and therefore lots of energy needed. Lots of energy needed to break. I know I've got the marks there. I'm not going to bother marking it. It usually, by the way, EdXL, that can be 4 to 5 marks, guys. You've just got to run it. Suggest why the melting point of silicon dioxide is higher than the melting point of sodium chloride. Covalent bonds in SiO2 are stronger than electrostatic attractions in sodium chloride. We're done. Saying that which one's got the stronger bonds. State why sodium chloride conducts electricity when molten, because ions are free, not electrons. The only people who have electrons are metals and graphite. Ions are free to move, to carry the charge through the structure. We know this question, seen it before. Through the structure. Carbon dioxide described as simple molecular substance. State why carbon dioxide is a gas at room temperature. Because there are wimps. Because weak intermolecular forces between molecules require little energy to break. Plenty of energy at room temperature to do that. Next, I think we're on to our last question, folks. 40 minutes in. I'm just waiting for my laptop to give me my question. Last question, number 15. I like it, all the calc. Okay, tick concordant results. Right, 0.2. So, no. Yes, yes. And I'm done. Okay, that's nice. Just checking, yep. Next, using the concordance, calculate the mean average of the volume added. Right, 2.0 plus 2, there you go, divided by 2, which gives me 2.15. I like it. Tick and tick. Show you working. Which is the most suitable piece of apparatus to measure out 25 centimeters of the solution? Oh, this is a titration. Measure out the solution into the conical flask. Pipette, only one. Yeah. Next. Right, calculate the moles in 20 centimeters cubed. Right. The mass of that in the 250 is that. The average volume of the solution added to 25 was 20. Concentration. Calculate the moles of potassium per well. There's its concentration, and the average volume added to 25 is that one. So number of moles is C. Sorry, I'm just turning my other computer back on in case someone has a question. Number of moles is C times V over 1,000. So concentration is 0.02. I'm actually going to do exactly what they've given me. Volume of 20.00 all over 1,000 gives me 0.02 multiplied by 20 all over 1,000. And I get 4 times 10 to the minus 4 moles. Holy moly, very small. Holy moly. See what I did there? Yeah. In the reaction, 1 mole reacts with 5 moles. So the ratio is 1 to 5 from KMNO4 to iron 2 sulfate. So I need to go from here to here, times by 5. I like it. Times it by 5. And that gives me 2 times 10 to the minus 3. I'm actually going to write over, I'm just going to move that and make it a bit clearer for them to see. Times 10 to the minus 4 times by 5. Gives me that number. Tick. Next, calculate the moles in the 250. Oh, did we take a sample by any chance? A dissolved sample is made up to 250. Measure out 25 of this solution. They're taking a sample, so it's going to multiply it by 10. Bring it back up, so I need to multiply that by 10, which is going to be 2 times 10 to the minus 2 times by 10. Yep, there we go, 0.02. Next, using your answer, calculate the mass in grams of sodium in that one. MR is that. Calculate the mass in grams of iron 2 sulfate in the... Okay, so that there, folks, is the moles of that guy. Well, okay. Number of moles is grams over rams. We know this. I've got grams. You've given me rams. No, but it's not. That's really clever. Everyone's going to do that, and they're going to get the number 1. We're not using that. We're using the moles. Reorganize. Number of moles times by rams gives me grams. I've got 2 times 10 to the minus 2 multiplied by 152 times by 152 gives me 3.04 grams. That makes sense. The rest of it's water. Another experiment has found that the 24.2 grams of iron contained that much of, calculate the mass of water. Okay, so 24.2 is the whole thing, and it contains that much of iron. I'm just going to minus it, 15.2, and it'll give me the water. Seems reasonable. 24.2 minus 15.2, and everyone's going to get that wrong. everyone's going to write down 9 and we're going to lose it. It needs to be 9.00, 3 sig fig at least. Yeah, it should probably be 1 decimal place, but they're going to say do not accept 9. First one I've seen in a while that I want to see an answer to. Yeah, covalent bonds have to be broken, large amounts of energy required. Covalent bonds in silicon are stronger than the ionic bond. Except covalent bonds are stronger than the ion. I hate that. Ions flow and move, except the ions are mobile. Yeah, it can move. Weak forces between molecules require very little energy. There we go. There's our average D per pet. Right. You guys tell me. Does that mean it's not required? Interesting. Okay, anyway. Let's go for that one. Calculate the amount in moles of water. Right, number of moles is grams over rams. And we all know that by now, everyone here knows that the MR of water is 18. At A level, by the way, 18.0, just letting you know. So I've got 0.5 moles. I'll write it on the line. Right, calculate the amount of moles of iron 2 in the 15.2 grams. Okay, that's fine. Number of moles is grams over rams. Look at that. It's a 10th. It's 0.1 in it. I'm still doing it on the calculator, though. I hope you realize that. I just don't trust myself. It's so easy to get arrogant. Don't do it. It's not worth it. Calculate a value for X. Right, so I've got Fe2O3. This is the same thing as empirical formula. H2O. Percent to grams, percent to mass, mass to moles. I've already got the moles. Yeah, I've got 0.1 of him, moles. And I've got 0.5 of him. Divide by the smallest to find the ratio. So 1 to 5, X is 5. And we're done. I think that's the end of the paper. It is. Let's bring it all back on board. Let's reactivate my camera. If it'll let me. It won't let me. Enable device. There we go. And then I bring it back to here. Look at that, 47 minutes. Let's go start camera. Let's bring it back online. There we go. Oh, might help if I turn it around. Front. Hello. Right, guys. There we go. I will leave you be for the rest of the day. Tomorrow, I'm going to blitz a paper 2, midday, 12 o'clock as normal. 2015 regional. I hope you found this useful, folks. It's been really good to see you guys. Keep working hard. Keep doing the papers. Yeah. I hope you guys have a great rest of your day. All right, guys. I'm trying to just find my way back to my tab. Guys, have a great day. See you later, folks.